switching gears from actually the last two subjects deal with both of the types of waves we talked about, sound waves and light waves. Sound waves, what kind of waves are they? Transverse or longitudinal? Sound waves are longitudinal. They're slinkies. I know. I think of long, like longitudinal, like this. So slinkies, that's sound. And so light waves are transverse, up and down, transverse. But they both do these last two things. And one, they're kind of, this is kind of intuitive. The whole thing about the dilution of the energy that's in the wave that's being transmitted. So think of the source here in the middle of these three kind of balls, these three spheres. As you go farther from the source, it becomes diluted. And each way, like the, how do I say this? This distance is R, this distance is R, and this distance is R. So you're stepping back R, R, and R. And each R that you step back, actually it dilutes the sound or the light by a factor of R squared. So it's not linear, it's to the second power. And that actually has to do with the fact that it's going out in all directions, not just this, it's going out in all directions. So it's called the inverse square law. You know, light gets diluted, sound gets diluted. So actually here I have the idea of sound getting diluted. So for instance, when we talk about weather, one of the things we're going to talk about is severe weather. And there's different types of lightning. One type of lightning is actually called heat lightning. And growing up, my dad and I enjoyed heat lightning. It's when you look out on the horizon and you kind of see the clouds kind of glowing, you know, kind of lighting up, but you don't hear anything, and that's a dilution issue. Basically, the sound got too diluted in order for it to get to you. That's heat lightning, and that distance is about 15 miles or so. So, very good. And actually, the video we watched talked about the scrunching up of waves. Remember we saw the train, where basically the train's going, ooh, you know, I'm coming, okay? So basically, the sound waves of the train in front of it are getting squished together. And one of the things we know about shorter wavelengths is the frequency goes up, the pitch goes up, okay? So it's kind of like if the train is coming and we're all listening, we'll hear the pitch go, nee, 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 nee. Actually, that was more of a car. I was thinking of a car coming towards you and the pitch goes up, and then when it passes you, the pitch goes down, okay? The colors, Roy G. Biv, like, what does that have to do with? This is called the Doppler effect. Roy G. Biv. Okay, which of these, red or violet, is the shortest wavelength? Violet, yep. And now, for whatever reason, when we call it blue, when basically the wavelengths are getting squished together because the source is moving towards you, like a car or train moving towards us, we call it a blue shift, not a violet shift. We should call it a violet shift, don't think of it. Okay? And then after it passes, when the wavelength is lengthened, we call that a red shift. Oh, so this is the longest. Yep. So, yeah. Now this actually can also happen with light. And when we talk about astronomy, in the field of studying the stars and the planets, especially the stars and the galaxies, we have to limit ourselves to kind of the energy coming from those faraway objects. And so we can actually we can't hear them, but we can see them. And we can see actually, if they're moving towards us, we can see a blue shift in their light. If they're moving away from us, we can see a red shift in their light. It is so cool. Okay, so there's kind of, what they call it, direct or indirectly? I think that'd be direct measurement of movement towards or away of a star. It's the same thing. But now I guess I should mention this car or this train that's moving towards you, creating like a squished wavelengths of sound. you're not going to necessarily see squished wavelengths of color from that car or that train. And the simple fact is, in order to get this, it's not moving fast enough to make that kind of color blur. But it can make the sound. Okay, so you guys already have these written down, right? So these will be due on Monday. Marvelous Monday. And the last thing I want to do is, if you have your notes, and if you don't, you'll just have to play along with me, but grab your notes for part 3. Grab your notes for part 3. And after the thing on, after I did that slide on energy, I went right to potential energy and I skipped kinetic energy. Because I was looking at my other course and I was like, wait a minute, I don't remember talking to my, you guys about kinetic energy. So for instance, if you find this slide, I think we watched the video and then called it a day. So if you find this slide, the slide after this slide, you have your notes, okay, I think it'll be fine. I think it's just 2 slides. The slide after this slide looks like this. Possibly we did. I just stopped there. But we did this right. Yay. So potential energy is stored energy, and kinetic energy is energy that's being spent, energy in motion. Potential energy is stored energy. It's like if you have the potential to do something, you could do it, or you could not do it. Kinetic energy, you're moving and doing it. So there's different ways to measure kinetic energy, and the one I want to look at is this one, where you know you have an object that's moving. M stands for mass, just like it does, and F is equal to MA. M stands for mass. What does V stand for? Velocity. Yep. So if you know the mass of the object and you know how fast it's going, its velocity, we'll square its velocity, take it times its mass, and take 1/2 of that. Kinetic energy is equal to 1/2 mv squared. Just rolls off at the tip of your tongue. So let's do a few problems. So kinetic energy of an object with a mass of 7 kilograms traveling with a velocity of 13 meters per second. And again, you're going to want to make sure we carry along the units as we work the problem. So I could pull out M is equal to 7 kilograms. V is equal to 13 meters per second. And then I'm ready to, as we do in a lot of things with physics, I'm just ready to plug these values in the formula. So kinetic energy is equal to 1/2 times the mass, which was 7 kilograms. Again, to get full credit on your test, or in your homework even, you need to make sure you include your units. And then we have 13, I'll put it this way, 13 meters over seconds raised to the second power. Now, if I just focus on the units, do you guys buy this? That what my units will be is kilograms, and then I'm going to have meters squared. So kilograms, meters squared, and I would usually put a dot between them. And then the bottom I'll have seconds squared. So that's what my units are. And this is where, if you're like, you can't find the square key or whatever, you can just take 13 times 13. That's the same thing as 13 squared. So. I get,
this what you guys get? I get what my calculator displays is 591.5 units would be kilograms meters squared per second squared. What units did I say energy was going to be in? Do you remember? Something you wear? Joules. Jewelry, joules. Yeah. Energy and work are all in joules. So actually, if we break the joule down, we talked about this the other day, the joule is kilograms meters squared per second squared. So you could go either joules or kilogram meter squared per second squared. It's like, really? You get a choice? Yes. So how many digits, looking back at the numbers here, 1/2, 7, and 13, how many digits should I be allowed? Just one, as far as I can tell. If we're doing it according to the rules that science uses. But if you wrote 592, you'd get it right. But I'm telling you, really, it's just one digit. So if it's just one digit, I'm gonna only keep this digit here. So do I leave it a 5 or round it up? Round it up. So that's why what I would do is actually just 600, and I could go with joules or kilograms meters squared per second squared. Either one is great. Okay. So on your note card, you're gonna, I don't know what your notes cards are gonna look like. Sometimes it's fun to see what your note cards look like. Oh, well, that's a good idea. Any questions about this? Okay, so an object with that mass traveling at that speed, so I think 13 meters per second, so 1,001, and it's got 13 meters. I wonder if each one of these is no, it's not quite a meter. But anyway, that's pretty fast. What if we have an object that's going the same speed, but it's more massive? Do you think the kinetic energy will increase or decrease? Yep, kinetic energy will increase. And it never hurts to look at it like this. Does that make sense? So let's knock this one out too. So here I have a different mass, 135 kilograms, the same velocity, 13 meters per second. My kinetic energy is equal to 1/2. The mass is 135 kilograms. The velocity is 13 meters per second squared. What my calculator displays is wow. I got 11407.5, and I'll go ahead and do joules. Cool. So, what should my answer be then? Just one digit, so it'd be 1,000,000,000,000. Does that look right? I think so. How would we pack that number up in scientific notation? This will be on the test too. Yep, 1 times 10 raised to the 4th power. Yep, units are joules. Perfect. Okay, let's see. Which object has the greater kinetic energy? Well, why? I think that question is kind of silly. The second one does because it's more massive. So these will also be due, or this one, I guess there's just one, exercise 12, so you probably don't have this one. Jot this down, exercise 12, and I will put this out on Twitter too. So on page 106, exercise number 12.
cool. Once you got that, that does it for a fly through physics, with just kind of an emphasis on a few things. We just dabbled. Weekends. Oh, did you get that?